In this video, we will be talking about what happens when gases are subject to extreme pressures. They cease behaving like ideal gases, and we call the phenomenon acting as a real gas. Looking back to the conceptual model that we're using that underpins the various laws that we have been talking about up till this point, the kinetic molecular theory, and from that, the ideal gas model. Right? The ideal gas model itself is based on the kinetic molecular theory. The kinetic molecular theory says that atoms can be thought of as these small hard spheres that are traveling through space, that they collide through elastic collisions, they are in ceaseless motion, right? And that the energy in them is stored translationally. So the ideal gas model uses the kinetic molecular theory and makes some additional assumptions. So one of the starting assumptions of the kinetic molecular theory is that atoms are in ceaseless motion. This is a fairly good assumption, a fairly good way of thinking about how the atoms are moving. This works as long as you're not decreasing the temperature down to about absolute zero. The energy is stored only in translational movement. There is no rotational or vibrational energy. Again, this is a very good assumption as long as you're not working at very low temperatures. When you're working at room temperature and above, the vast majority of the energy is being stored in translational. The rotational and vibrational components only make up a very small subcomponent. And so realistically, this is a good assumption. It eases the math and will help things out. Atoms undergo elastic collision. That is perfectly valid. There are no intermolecular forces acting on the atoms. This is a very large assumption. And we know that if we're working with charged species, there is going to be intermolecular forces. Also, if our species exhibit things like hydrogen bonding, that's a strong intermolecular force, and that should have some sort of an effect on our molecules. But if they are far away from each other, intermolecular forces die off fairly quickly with distance. And so as long as we're talking about gases that are not under high pressure conditions through compression, i.e. they're taking up very small volume, the molecules themselves are fairly far apart, and so this is a good assumption. Atoms take up no volume as long as you're working at low pressure, where the vast majority of the space is empty, and the volume that molecules actually do take up is insignificant compared to the total volume. This is a good assumption. However, if we start working under either low temperature conditions, some of our first assumptions break down, or if we're working under very, very high pressure from compression, another way of thinking about that is very low volume, some of these other assumptions break down. If we're working at high pressure through low volume, the molecules are going to be close to each other, and so we will have intermolecular forces interacting with each other. The atoms themselves will take up volume. So when we compress our gases to fairly high pressures, like 10 atmospheres and above, there are going to be intermolecular forces that will interact on the atoms. And so we have to have a way of taking this into account. Also, the atoms themselves do take up volume. So if we compress the molecules such that the space that they're flying around in is similar to the size that the atoms take up, then the volume that the atoms do occupy will become relevant. If we think about real gases using actual molecules, molecules themselves do actually occupy space. So because real molecules take up space, the molar volume, or the volume that 1 mole occupies of a real gas, is going to be larger than is predicted by the ideal gas law at high pressures. And this is because you have the molecules, they're occupying space, and so the volume that you'll get, the volume that you will find that gives you a particular pressure is higher because the amount of space that the atoms travel between collisions is actually less than what you would predict based on the ideal gas law, which uses the ideal gas model that says that the atoms take up no space. So because they take up space, they will collide more frequently, and that frequency becomes important if you're working at very low volumes and very high pressures. So if we look at the molar volume, the amount of space that 1 mole occupies in liters at very high pressures. So on our x-axis, we're looking at 200, 400, 600, 800, 1,000 atmospheres of pressure. This is quite a lot of pressure. The ideal gas is the red line here. And even something like argon, right? Argon is just, because it's a noble gas, it won't form bonds. And so we're just talking about the argon atoms themselves, not a larger molecule. When you start to get to very high pressures, what you'll find is that the volume that is occupied, or the volume that you will find to get to a particular pressure, is higher than you would predict based on the ideal gas model. So for example, at 600 atmospheres of pressure, you might predict that the volume is here at somewhere around 0.07, but you're actually measuring 0.08 liters, right? So the volume is higher than what you would expect. Another place where this could be a problem is if you have a container and you're trying to reach a certain pressure based on a volume. If you make the container too small, thinking that if you need a 0.1 liter container to achieve 400 atmospheres of pressure, you'd think here, but what you would actually be getting in terms of the pressure at that 0.1 liter volume is over here. So you're looking at about 425 atmospheres of pressure as opposed to the 400 that you thought you were going to work with. This can cause problems under industrial settings. So it was in 1873 that Johann von der Waals modified the ideal gas equation to be able to fit some of the behaviors of real gas at high pressure, essentially coming up with a bit of a modification factor to the volume. So the molecular volumes actually take up space. So because the molecular volumes makes up a real volume that is larger than what the ideal gas would predict, we need to be able to take that into account. So what van der Waals did was he added this B term to our ideal gas equation. So if you take the ideal gas equation, solve for volume, what he did was took this particular term which takes into account the space that the atoms take up. So the NB is the number of moles of atoms you have times essentially how big the molecules are. When you're looking up these van der Waals constants, what you'll find is that for larger molecules, the B value is bigger, and that will subtract more off of your volume, giving you a higher pressure at a lower effective volume. So essentially you have to get to the volume that you'll use to get to a particular pressure is higher than what you would have predicted otherwise. All right, so essentially this NB term takes into account the volume that the molecules actually occupy. Now, van der Waals also modified it for intermolecular forces. So if you have a molecule, you got to think of the pressure as being the molecules slamming against the wall of the container. So if the red dot here is an atom, when it collides with the side of the container and changes its momentum, that's what we measure as pressure. If there are intermolecular forces, they will typically pull the molecule towards the center. Those are attractive forces. So if you have an attractive force, because there aren't any of those molecules on the wall, the center of the container is where the net force of those attractive forces will pull the molecules that are close to the wall. So it has this effect of pulling them away from the wall, which reduces the amount of energy that they're striking the wall with. So because there's a force pulling them towards the center, the pressure actually gets reduced. That's for attractive forces. You could also have repulsive forces. So if all of your gases, for example, had a charge to them, they would push each other away. And so if you have a repulsive force, then the center is pushing outward, which means that the molecules are going to hit the wall with more force than you would predict based on how many atoms there are in the form of number of moles and the volume that you're working with. So what van der Waals did was he added this A term that accounts for pressure. So the pressure plus this intermolecular force attraction value, which will be multiplied by the square of the density of the atoms. So the more densely packed the atoms are, the more atoms per more atoms per unit volume, the bigger this effect is going to be. And it's squared because they're interacting between themselves. So if you have atom A over here, atom B over there, the higher the concentration of your particular atoms, the more interactions they're going to have, and so it goes by the square. What we see is that for things like xenon, when the temperature decreases, the molecules are moving slower. So if we look at pressure versus temperature, where we really see the divergence from the ideal gas behavior is at low temperature. The reason why it is occurring more at low temperature is the molecules are moving slower, which means they have more time to interact with each other. So if there's an attractive force, because they're moving slower, they're going to feel the attractive force more, and so the effect of the attractive force pulling the molecules into the center of your container will be greater at low temperature than it will be at high temperature. So essentially you will see more of an effect of intermolecular forces. So something like xenon itself doesn't have very strong intermolecular forces. It's attracted via van der Waals, where the electrons on the xenon atom, they shift around, and at some points they can be on one side of the nucleus, which would cause a net positive side, and a net negative side, which can cause the xenon atoms next to them to do the same, and you get that temporary dispersion force interaction. So xenon doesn't have very strong effect, or doesn't have very strong intermolecular forces, but it will itself actually show this effect of the attractive forces. So even something like xenon, which doesn't have strong attractive force, at low temperature and fairly high pressure, we're talking 10, 20 atmospheres, down at 200 Kelvin, you can get an appreciable effect that, if you don't take that into account, can cause problems. So we can put these two together to get what we call the van der Waals equation. So combining the component here that the atoms actually take up space, that's this B term, the space that the molecules actually take up, and the correction for the intermolecular forces, we get an equation that looks like this. More commonly, what happens is we rearrange this to move the volume to the other side, and then subtract this attractive force from both sides, leaving us with the more common method for showing the van der Waals equation, which is P is equal to nRT over V minus NB, quantity, the whole thing, minus A times the quantity N over V N parentheses squared, right? So this term here is our van der Waals equation. What this does for us is it allows us to take into account the size of the molecules through the NB term that's down on the bottom, and it allows us to take account for the intermolecular forces, right? So if the molecules themselves take up a lot of space, that will reduce this volume term. As the volume goes down, as the term here goes down, the pressure will go up, right, because the volume's on the bottom. So as the effective volume goes down, the pressure goes up, which means because the atoms take up more space, right, the pressure should be higher. Here, this is the attractive force. As the attractive force increases, right, that's going to pull the molecules towards the center, which decreases the pressure. So you have this minus A times quantity N over V squared. So as the attractive force increases, the pressure should decrease, which is what we end up seeing. So if we try to see what effect this van der Waals interactions, or the van der Waals equation, has on real gases, what we can do is look to see how much they deviate from ideal gas behavior. So what we typically do is we plot something like pressure, how much we're compressing the gas, versus the ratio of PV over RT. The reason we're using this ratio is if we grab 1 mole of substance and we start compressing it or expanding it, right? PV, pressure times volume, over RT, this should equal whatever the number of moles are, right? This is our equation for number of moles if we rearrange the ideal gas equation. If we're using 1 mole of substance, we should get a value of 1. So if the attractive forces dominate, what that's going to do is pull the molecule in towards the center of the container, decreasing the pressure. Because the pressure term goes down, the whole value of the ratio becomes less than 1. We measure a ratio that's less than what it should be. This ratio, if we're using 1 mole, should give us a value of 1. So if there are attractive forces, that's decreasing the pressure below what it should be, making the top value less than the bottom value, which gives us a value less than 1. So if on this graph our values dip below 1, what that means is that we are attractive force dominated, right? You have attractive forces which are taking over, pulling the molecules towards the center. Now, if on the other hand we have repulsive forces, which is much less common, or we have molecular volumes that we're compressing the molecule enough that the size of the atoms becomes important, what that will do is that will increase the top term. So if we have repulsive forces, the P is bigger, right? Because if it's a repulsive force, it's pushing the molecules towards the walls of the container. Or if we have the molecular volume increasing because the atoms themselves actually occupy some space, the top term will go up, making the value bigger than 1. So let's look at helium. Helium has very weak intermolecular forces. So we're not really going to see much of an attractive force in the molecules, but helium does take up space. So when you compress helium a lot, what you'll see is very little effective intermolecular forces, and instead this is pretty well dominated by the volume, the molecular volume that the helium take up. Neon, right, it's also noble gas, so it won't have very strong intermolecular forces, but it does have a lot of electrons, which means they're able to shift to one or the other of the sides of the molecules more than helium does. So what that means is that the dispersion forces, the intermolecular forces, the attractive forces of neon are going to be stronger than helium, which is why the value here for our ratio of PV over RT at very high pressures for neon is less than it is for helium. Helium doesn't have very much intermolecular forces at all. Neon doesn't have a lot, but it has more than helium does. Argon is another noble gas, but here argon is bigger than neon. It does have some attractive forces. So because the electrons in argon are able to shift even more than they do in neon, we actually see a little bit of a curvature here, and that's coming from that A value in the van der Waals equation, and because it's N over V squared, you get a little bit more of this curve going to it. Xenon is the next one down from argon, so it has even more electrons, and so the van der Waals interaction is even stronger. If we had an ideal gas, it would be 1 no matter what we do. The last one we have on this graph is water. Water has a very strong intermolecular force, right? Hydrogen bonding. So if we compress water molecules really, really close together, they're going to have that strong attractive force, which means that it's going to be attraction force dominated. The pressure will be less than what we think because there's going to be attractive force pulling the atoms in towards the center, right? So our value of this ratio is going to be less than 1, which is what we see. We can actually see that it drops quite a bit down below what we think it should be, and the reason it does it so much is because water has that hydrogen bonding, which is a very strong intermolecular force. Let's now look at a problem that uses the van der Waals equation. So let's say we're trying to determine what is the pressure of chlorine gas in a 1.20 liter container with 15.0 moles of Cl2 of chlorine gas heated to 504 Kelvin using both the ideal gas and the van der Waals equations. So essentially we're going to compare the results that we get using the ideal gas equation and the van der Waals equation. Okay, so let's do the ideal gas first. So under ideal conditions, our ideal gas, we're going to use our equation PV equals nRT. We're trying to find the pressure, so we're going to move volume to the other side. That cancels out volume on the left, which gives us pressure is equal to nRT over V. Okay, so we can plug in our values. Our N value is 15.0 moles. We're going to use a slightly different R value. We're going to use one because we have liters and we have bar. I'm going to use an R value that has liters in bar. So we're going to be using 0.08314 liter bar per mole Kelvin. Okay, and then I'm going to take this, multiply this by our temperature, 504 Kelvin. Take all that and divide it by our volume, which is 1.20 liters. Canceling things out, our moles cancel out, our Kelvin cancels out, our liters cancel out, which would leave us with bar. If you plug this in to the calculator, you'll get 500. This will equal 523.782 bar. That is an 8. Okay, in terms of our significant figures, our moles has 3, our volume has 3, and our temperature has 3. And so our end answer will have 3 significant figures. So our value, our pressure for ideal gas would be 524, right, because the 7 rounds up, bar. This is the pressure we would expect using the ideal gas equation. If we use our van der Waals, right, if we use the van der Waals equation, let's see what we come up with. So the van der Waals is pressure is equal to nRT over V minus NB minus A times N over V squared. Okay, so plugging our values in, we have our pressure is equal to our 15.0 moles times, I'm again going to use the R that we had before, so that's 0.08314 liter bar per mole Kelvin. Our moles cancel out. We then multiply this by our temperature, 504 Kelvin. Our Kelvin cancels out. We will take this whole thing, divide that by V minus NB. So our V, our volume, is 1.20. Our N, so we're going to minus N, 15.0. Our B value is listed up here. So for these, you would actually have to be given the values. So N times B, and to make sure that we do the N times B first, we'll chuck it in a set of parentheses, 0.05622 liters per mole. The units on the 15 are mole, and so our moles would cancel out, giving us liters. Our unit here is liters, so we're taking liters minus liters, which is good because in order to do addition subtraction, your units have to agree. Okay, so up here, our liters will actually cancel out the unit that we would get left with here. So our liters up top cancels out the liters on bottom, so that works out. We now subtract our A times the quantity N over V squared. So our A is also listed up top. This value would also have to be given to you. So that is 6.579 liters squared bar over mole squared. We're going to take this and we're going to multiply it by N over V, so 15.0 moles, over V, 1.20 liters, quantity squared. If we look at our units, the liters squared here will cancel out the liters here. The mole squared on bottom will cancel out the moles here. And so we're left with bar, which is good because we're doing subtraction. So in order to do addition subtraction, your units have to agree. On the left-hand term, we have bar. The right-hand term, we also have bar. If you carefully plug this into your calculator, right, your pressure is going to equal, the left-hand term would be 1,762.0925 bar. Then we're subtracting the second term, which would be 102.7968 bar, which gives us 734.1237. Okay, our terms, in terms of number of significant figures, you'll find from the left-hand side, we have 3 sig figs up top. On bottom, we're going to end up with also 3. So our first part has 3 sig figs. Our second part is going to also have 3 significant figures from here. Right? So when you subtract, it's the least number of decimal places, so we will have to cut it in the tens place. So it ends up getting cut there. So our pressure, what you will actually measure is 730 bar of pressure, right? So you can see that using the van der Waals equation, for real gases, you do get a significant difference between the two values. And if you were trying to design a container for this particular reaction or whatever you were doing, and you use the ideal gas equation, you would end up with a ruptured tank at a very high pressure. This would be very, very bad. Okay, so the van der Waals equation takes into account the size of the atoms or molecules and the intermolecular attractive or repulsive forces that they are undergoing. In order to do a van der Waals equation, you would need to look up the A and B term, or on a test, you would be given the A and B terms.